Hello everyone! In this video, we are going to show you how to solve a linear programming problem. First, let's have a little review. What is linear programming? Linear programming, or LP, is a widely used mathematical modeling technique designed to help managers in planning and decision-making relative to resource allocation. Despite its name, LP and the more general category of techniques called mathematical programming have very little to do with computer programming. In the world of management science, programming refers to modeling and solving a problem mathematically. Computer programming has of course played an important role in the advancement and use of LP. Real-life LP problems are too cumbersome to solve by hand or with a calculator. Now, here are the steps in formulating a linear program.
First is to completely understand the managerial problem being faced. The furniture manufacturer's problem is to determine the best combination of chairs and sofas to manufacture in order to reach maximum profit. First, we summarize the problem in a table manner to understand the problem better. This problem is a type of product mix problem, wherein two or more products are usually produced using limited resources such as personnel, machines, raw materials, and so on. Second is identify the objective and the constraints. Now we identify the objective and the constraints of the problem. The firm's objective is to maximize profit, and the constraints identified in the problem are: first one, we have the factory has allocated at most 66 labor hours for carpentry. Second is 180 labor hours for finishing. Third is the 200 labor hours for upholstery. And lastly, the non-negativity constraints. The third step is define the decision variables. Decision variables are variables that represents the actual decisions we will make. For this problem, it is defined as X as the number of chairs produced and Y as the number of sofas produced. The fourth step is use the decision variables to write mathematical expressions for the objective function and the constraints. We can now create the LP objective function and constraints in terms of X and Y, and it will now look like this. Maximize Z, which is equal to 90X plus 75Y, subject to 3X plus 2Y less than or equal to 66 for the constraints of carpentry, 9X plus 4Y less than or equal to 180 for the constraint of finishing, 2X plus 10Y less than or equal to 200 constraints for the upholstery, and X and Y greater than 0 for non-negativity. In this video, we use one method to solve the LP problem of the furniture company through graphical solution approach. The graphical method works only when there are two decision variables, but it provides valuable insights into how larger problems are structured. When we recall to our algebra, we expect that linear equation in two variables is a straight line. Now we solve for the values of x and y of each constraint. For constraint 1, 3x plus 2y which is equal to 66, will let x which is equal to 0 would result into y which is equal to 33, and let y which is equal to 0 and could make x which is equal to 22. For constraint 2, 9x plus 4y which is equal to 180, let x which is equal to 0, then y equals to 45, let y is equal to 0, then x is equal to 20. For constraint 3, 2x plus 10y which is equal to 200, let x which is equal to 0, then y is equal to 20, let y which is equal to 0, then x is equal to 100. Plotting each constraints, it will now look like this. This is now the feasible region. We shade the region where the area of solutions that does not exceed either of the three furniture manufacturers' constraints. This area is called the feasible region. This represents that any point within the feasible region satisfies the conditions of the constraints. Any point outside the shaded area would represent an infeasible solution. There are two methods in finding the optimal solution after solving the graphical solution method. We have isoprofit line method and corner point solution method. We use corner point method. We then substitute the values of x and y on the objective function to get the z value or the optimal solution. Since our objective is to maximize the profit, we select the corner with the highest profit in this problem. The highest profit is found to be $2,250, which is obtained when 10 chairs and 18 sofas are produced.
The second problem is a minimization problem. The farmer's problem is that he wants to determine the low-cost feed for the animals that meets the minimum daily requirement for each nutritional ingredient. First, we summarize the problem in a table manner to understand the problem better. Now, we assign the decision variables. X is the number of type A bags produced, y as the number of type B bags produced. We then identify the objective and the constraints of the problem. The farmer's objective is to minimize cost. The objective function will then be minimize z is equals to 10x plus 12b. And the constraints identified in the problem are minimum daily requirements of 150 units of proteins, minimum daily requirements of 90 units of minerals, minimum daily requirements of 60 units of vitamins, and the non-negativity constraint. The constraints are 40x plus 30y is greater than or equal to 150, and this will be the constraint for proteins. 20x plus 20y is greater than or equal to 90 is the constraint for minerals. 10x plus 30y is greater than or equal to 60 is the constraint for vitamins, and the non-negativity constraint. Using the corner point method on a minimization problem, we first construct the feasible solution region by plotting each of the constraints. For constraint 1, 40x plus 30y is equals to 150. Let x be 0, y is equals to 5. Let y be 0, x is equals to 3.75. For constraint 2, 20x plus 20y is equal to 90. Let x be 0, y is equal to 4.5. Let y be 0, x is equal to 4.5. For constraint 3, 10x plus 30y is equal to 60. Let x be 0, y is equals to 2. Let y be 0, x is equals to 6. Plotting the coordinates, it will now look like this. We then identify the feasible region. Note that minimization problems often have unbounded feasible regions. For corner A, we have coordinates 0 and 5. For corner B, we have coordinates 1.5 and 3. For corner C, 3.75 and 0.75. For corner D, 6 and 0. When we already have identified the corner points, we can now calculate the value of the objective function at each corner points. We substitute the x and y value of the points to our objective function equation to get the optimal value. Since our objective is to minimize profit, we select the corner with the lowest cost in this problem. The lowest cost is found to be $46.5, which is obtained when 10 type A and 12 type B of low-cost feed are produced.